Hello guys, you are welcome to the platform once again. My name is Green, and in today's lesson, in today's video, we are going to be looking at something very essential in physics. This topic is actually useful for you if you are writing JAM, if you are writing WAEC, if you are also in your 100 level in the university or in the college. This topic is very essential for you, and that is reflection of light. Reflection of light is a concept under the big guy, which is optics. So I'm going to be starting from what optics is all about and what you need to know as regards optics before we now move straight to what we call reflection of light. So let's begin. All right, when we talk about optics in physics, what exactly is optics? Optics is just a branch of physics that deals with the study of light, and that's all. Optics is a branch of physics that deals with the study of light. So that means that we are introducing another concept, which is light. So what exactly is light? All right, so when we talk about light in physics, we need to talk about the electromagnetic waves. And what are the electromagnetic waves? If I remember, the spectrum is given as the radio wave, the microwave, infrared, visible, X-ray, and gamma ray. This is the electromagnetic spectrum. And in this spectrum, this arrangement is in the order of increasing frequency. So all of these are electromagnetic waves. And this is the order of increasing frequency of these waves, while this is the order of decreasing wavelength. Decreasing wavelength. That means that in terms of frequency, radio wave has the lowest frequency, while gamma rays have the highest frequency. While in terms of wavelength, the gamma ray has the shortest wavelength, while the radio wave has the longest wavelength. Now, why are we talking about this electromagnetic spectrum? Because we want to describe light. We said optics is a branch of physics that deals with the study of light. What exactly is light? Light is a portion of the electromagnetic spectrum that is visible to the human eye, that enables us to see objects. So out of these 1, 2, 3, 4, 5, 6, 7, we have a portion which is usually between, because this is the order of decreasing wavelength, is around 4,000 angstrom to about 8,000 angstrom. That's the range of the wavelength. Angstrom means 10 to the power minus 10 meters. That's angstrom. So a portion of the electromagnetic spectrum, which means this visible light region, that is visible to the human eye, that enables us to see objects, is what we call light. Light is a region, a portion of this spectrum, of these EM waves, of this oscillating electric field and magnetic field that the human eye can see, that enables us to see objects. So that is what we are studying in optics. That is what optics is all about. It is a study of light, and light that we are talking about is this region of the electromagnetic spectrum that the human eye can see. Now, in the concept of optics, we have two categories when we are dealing with optics. We can talk about optics in terms of geometrical optics. We have geometrical optics, which is also called ray optics. And we have wave optics. So we can study light in two ways, in terms of the rays and in terms of the waves. But what exactly is this geometrical optics? So whenever we are studying light and we are dealing with objects, we are dealing with instruments whose diameter is actually far, far greater than the wavelength of the light. When the diameter of the objects that we are dealing with, objects like the mirror, the plane mirror, the curved mirrors, objects like your simple microscope, your telescope, the diameter of these objects are far, far greater than the wavelength of light, of the visible light. Look at the wavelength of the light. It's in the order of 10 raised to power minus 10 meters. So the diameters of these guys here are actually far, far greater than the wavelength of light. So when we are talking about that aspect of optics, then we are dealing with geometrical optics. So this is where we talk about reflection of light, refraction of light, the concept of prism, triangular prism, rectangular prism, the concept of lenses. That is everything we talk about here. Our optical instruments, the microscopes, the telescopes, and all of that. That is what we discuss under geometrical optics. That means that the aspect of optics that I want to talk about in reflection of light is just our ray optics, that is the geometric optics. Then we have the other aspect of optics where we deal with objects whose diameter is actually comparable. The diameter is comparable to the wavelength of light. In this region, that is where we talk about the concept of interference, patterns of light, where we can talk about the Young's double slit experiment and the likes. We talk about diffraction patterns here. We talk about polarization in this case. Polarization here, because the objects that we are using, which is usually our basic slits, small openings, the diameter of these guys are actually comparable to the wavelength of the light that we are considering. So that implies that the aspect of optics that I want to talk about in this lesson is just geometrical, or the ray optics, the study of optics through the usage of the ray of light, which means the path followed by light. So let's begin properly with reflection of light. Reflection of light. So reflection is one of the properties. Reflection is one of the properties of a wave. Light is a wave and it's also a particle, but then we are talking about only the wave nature here. So reflection is a property of light. Reflection is also a property of any wave at all. So when we talk about reflection, we are talking about the ability. Reflection is the ability of light to bounce back. Ability of light to bounce back after being incident on the surface or a barrier, and that is reflection. So what are we saying? If I have a barrier, so to speak, if this is a barrier, which could be a plane mirror, and light ray is incident on this guy, a ray of light is incident on this guy, this is a medium, so light is traveling through air. This medium, this glass here, is another medium entirely. So when light strikes this guy, it is incident at this particular point and it bounces back into air. It did not enter into this particular medium. It bounces back into air. Then this ability or this property of light to actually behave in this manner is what we call reflection. The ability of light ray to bounce back after being incident on a surface, after being incident on a barrier, is what we call reflection of light. All right. So we have spoken about some important concepts here. The first concept I mentioned now is what we call ray of light. Ray. What is ray of light? Ray of light is just the path taken, the path followed. The path followed or the path taken by light. The path followed by light is what we call ray of light. So if I say, okay, light, and from what we call the rectilinear propagation of light, there's something called rectilinear. There's a concept called rectilinear propagation of light. Light will always travel in a straight line. According to this theory, light always travels in a straight line. Light cannot be bending like this. It travels in a straight line. So the path that is followed by that light is what we call a ray of light. So if light is moving like this, that path followed is what we call a ray of light. That is what we call a ray of light. So what we talk about, when we talk about reflection of light, we are talking about the ability of light to bounce back. This light is incident on this board, then it bounces back. It is not penetrating into the board, it is bouncing off the board. That ability is what we call reflection of light. And the path followed by that light is what we call a ray of light. Now we also have what we call a beam of light. What is a beam of light? A beam is just a bundle or collection, bundle of light rays. Collection of rays of light is what we call a beam of light. So if I have several rays of light together like this, this is a beam of light. In fact, we call this a parallel beam of light because all the rays of light are moving in the same direction and they are not actually intersecting. This is a parallel beam of light. We can also have a convergent beam. Convergent beam, where all the rays of light coming from different sources actually meet at a point. This is also what? A collection of rays, but then they are all meeting at a singular point. We call this a convergent beam. Beam of light can also move out from a singular point. They are going out from a singular point. they are going out from a singular point. The rays are going out from a singular point. This is what we call a divergent beam. A divergent beam. So generally, a beam of light is just a bundle or collection of light rays. And it can be parallel, it can be convergent, it can be divergent. While the ray of light is the path taken by that light. And when we talk about rectilinear propagation of light, we are talking about the ability of light to travel in a straight line. Light travels only in a straight line. So that is what we call reflection of light. All right. Before we go on to talking about what most of you are usually interested in, talking about mirrors, talking about curved mirrors, plane mirrors, and the likes, let's quickly talk about the types of reflection that we can have and the laws of reflection of light. Very quickly. Types of reflection, and the laws of reflection. So we understand that reflection is the ability of light to bounce back after being incident on a surface. Light is traveling from air, then it hits this particular guy and bounces back into air. That property is what we call reflection. There are two types of reflection. Types of reflection of light. Reflection can occur in two ways. There are two types. We have the regular reflection or the specular. Reflection can be regular or specular, and reflection can be irregular or diffused. Reflection can be irregular or diffused. Now, this classification of reflection into regular and irregular is actually based on the nature of the reflecting surface. It is the nature of reflecting surface that will determine whether we are going to get a regular reflection or an irregular reflection. If the reflecting surface is a smooth reflecting surface, like the surface of a plane mirror, then the kind of reflection we are going to get is a regular reflection. But if the reflecting surface is rough, then we are going to be getting an irregular or a diffused reflection. Like the pages of a book. If light ray falls on the page of a book, because of the roughness of that surface, you are going to be getting an irregular reflection. Let me show you with a diagram. So if I have a smooth reflecting surface like the surface of a plane mirror, and rays of light, that is the beam of light, coming from a source, strikes this guy. Upon reflection, they will all move off in an irregular manner, in a regular fashion, parallel to each other. And why is this happening? Because the reflecting surface is smooth. This is a smooth reflecting surface, and it will give us regular reflection. But if I have a rough reflecting surface, like so, when we have rays of light incident on this guy, then they will move off in an irregular fashion. One can go up like this, another one can go like this. Even though they are still moving off in a straight line, but the reflection is not actually regular. Now, it is important to know that the rays that are coming from the source, incident on this guy, we call these rays the incident rays. These are the incident rays. While after reflection, the rays that move off are called the reflected rays. These are the reflected rays. So we have the incident rays and we have the reflected rays. So these are the two types of reflection that we have. We can have the regular reflection and we can have the irregular or diffused reflection, depending on the nature of the reflecting surface, whether it is a smooth reflecting surface or it's a rough reflecting surface. And that is all about types of reflection. All right, let's move on to the laws of reflection. Laws of reflection. All right, so I'll be using a smooth surface to actually explain the laws of reflection. So if I have a smooth reflecting surface, for instance, a plane mirror, and we have a ray of light that is incident on this guy, like so, and we draw a perpendicular line to this surface. This is a perpendicular line to this surface, a line making angle 90 degrees with the surface. Of course, we are going to be getting a reflection like so. So this ray of light is called the incident ray. This is the incident ray. ray coming from our source. This is the reflected ray. This is our reflected ray. And this perpendicular line, this line that makes an angle of 90 degrees with this plane, is called the normal. This is the normal. Right? There are two laws of reflection that you are expected to know. The first law of reflection is telling us that the incident ray, the reflected ray, and the normal at the point of incidence must all lie in the same plane. Now, most students don't usually understand this concept of lying in the same plane. And let me try to explain. Let me explain that plane that we are talking about. If I have the incident ray coming from the source like so, we have the normal coming from the normal drawn perpendicular to the reflecting surface like so. We are saying that the reflected ray must also be within this XY plane, within this dimension. There is no way the incident ray will be coming like this, the normal will be perpendicular like this, and the reflected ray will be going out like this. No, it's not possible. We can't have the reflected ray going out like this. We can't have the reflected ray going inwards into the plane. They must all be on this same plane, on this same XY plane. That is what we are saying. We can't have the incident like this and the normal like this. We can't have the incident like this, the normal like this, and the reflected outside like this. It is not possible. So the first law is saying that what? The incident ray, the reflected ray, and the normal at the point of incidence, all lie in the same plane. They are all in the same plane. That's the first law. Now the second law, which is extremely important, is, now let's go back to our diagram first before we talk about the second law. This is the incident ray and this is the normal. There is an angle between the incident ray and the normal. The angle made between the incident ray and the normal is called the angle of incidence. I is the angle of incidence. Angle of incidence is the angle between the incident ray and the normal. Similarly, there is an angle between the reflected ray and the normal. That is denoted by R, and R is called the angle of reflection. Angle of reflection. There is also an angle between the incident ray and the surface. We call it the glancing angle, G. There's an angle between the reflected ray and the surface. We call it the glancing angle, G. So G in this diagram is the glancing angle. Glancing angle. Angle between the incident ray and the surface, or the reflected ray and the surface. Now, what the second law is saying is that the angle of incidence, I, must always be equal, to the angle of reflection. That is the second law, which is very important. The angle of incidence must always be equal to the angle of reflection. In your exam, they might not mention that, oh, I is the angle of incidence. They might tell you that the angle between the normal and the incident ray is 50 degrees. Don't forget, incident angle of incidence is the angle between the incident ray and the normal. And angle of reflection is the angle between the reflected ray and the normal. The two guys must always be equal to each other. So that means that what? If this guy makes an angle of 50 degrees with the normal, then the reflected ray will also make an angle of what? 50 degrees with the normal. And if you are told that the incident ray makes an angle of 35 degrees with the surface, if an incident ray makes an angle of 35 degrees with the surface, what is the angle of reflection? So if this angle here is 35, angle with the surface is the glancing angle. So if this guy here is 35, then the remaining angle here should give me 55, because the whole of this is 90. So this is 55 degrees. Then automatically the angle of reflection will also be 55 degrees, and the angle here will also be what? 35 degrees. So the second law is telling us that the angle of incidence must always equal to the angle of reflection, and it's important you take note of that. All right, so let's move on to what we call angle of deviation. Angle of deviation. Angle of deviation. So there's something also called angle of deviation. Angle of deviation. If you have a plane mirror, this is a plane mirror, a plane surface. This is the normal to the surface. Then we have the incident ray, we have the reflected ray, the incident, angle of incidence, angle of reflection. We can be asked to determine the what? Angle of deviation. What is the angle of deviation? And one thing you should note about angle of deviation is that it is not just for mirrors. It's the same concept in refraction of light, in lenses, in our prisms. It's the same concept in both rectangular prism and triangular prism. Same idea of angle of deviation everywhere. This is the incident ray of light. Incident. Why do we have a reflection here? We have a reflection here because of the silver portion that we have on this mirror. The silver, we just have a glass. A mirror is just a glass, and we silver one portion of the glass. We coat one portion of the glass with silver. Then it now began to what? To actually reflect. Now, the concept of angle of deviation is this. This is the incident ray of light. Let's assume that this reflecting surface is not there. That means that this incident ray of light is supposed to continue like so. If we don't have this reflecting surface, then the incident ray of light is supposed to travel and continue like this, because remember, a ray of light is supposed to travel in a straight line. So without the presence of this reflecting surface, the incident ray is supposed to continue this way. But because we have the reflecting surface, there was reflection. We have our reflected ray in this direction. Now, the angle of deviation is now the angle between where that incident ray was supposed to pass in the absence of a reflecting surface, meaning here, and where it eventually passed in form of a reflected ray, meaning angle between this point and this. That is the angle of deviation we are talking about. The angle from here to here is the angle of deviation. Very easy. So how do we calculate this angle of deviation? There are so many ways, so we use delta to represent angle of deviation. So how do we get this delta, which is angle of deviation? If you look at this is a straight line, this is a straight line, and the sum of the angles on this straight line should give us 180 degrees. So that means that if I add I plus R plus this angle of deviation, I should get 180 degree. Meaning we are saying I plus R plus delta should be 180 degree. So if I make delta subject of the formula, delta will be 180 minus, then we can transfer this over here, minus I minus R, which is similar to saying 180 degrees minus I plus R. I will add my I and R together, then subtract it from what? 180. That will give me the angle of deviation. Very easy. Very easy. But then, there is another way we can get our angle of deviation, because of course, there are so many ways to solving problems. Remember in this diagram, I call these angles here glancing angle. Angle of glance. The angle between the incident ray and the surface, and the reflected ray and the surface is our glancing angle. Meaning that this small angle here is G, the angle of glance. The angle here is our G, our angle of glance. Similarly, the angle here is our G. From our basic knowledge of mathematics, from here, if this is G, this should also be G. Vertically opposite angles are equal. If this is G, then this angle here, this one alone, should also be G. So this guy is also G. So if this is G, this is also G. And the entire angle here is our angle of deviation. That is to show that what? Angle of deviation should just be what? G plus G. So our angle of deviation delta is just what? G plus G, which is just what? 2G. That is angle of deviation. That is another way we can get angle of deviation. So the angle of deviation is the angle between where this incident ray was supposed to pass without the angle or without the reflecting surface being there, and where it eventually passed in form of the reflected ray. Or if the mirror is actually faulty. So another way you can actually see question on angle of deviation is if a faulty mirror is used. If a faulty mirror is used, it means that this portion might not be silvered. That's a faulty mirror. That means that this ray of light that is passing, that is going from the source to this point here, instead of being reflected like this, it will continue. That's a faulty mirror. So when a faulty mirror is used, there will be an angle of deviation that you'll be asked to calculate the angle of deviation, which is just what? Twice of the glancing angle. What is the glancing angle again? Angle between the incident ray and the surface, reflected ray and the surface, or 180 minus the sum of the angle of incidence and the angle of reflection. And don't forget, these two guys are always equal to each other. So I can say 180 minus 2i or 180 minus 2r. So that is what we call angle of deviation. It's as easy as that. Let's progress to the next concept. The next concept is image formation. Image formation on a plane surface. Now let me now use the plane surface as a plane mirror. What are the properties of the image that will be produced by a plane mirror? Very important to know this. What are the properties? What are the kinds of images that can be formed on a plane mirror? So you need to know all of these guys. Number one, based on the type of image that can be produced, the plane mirror will always give us a virtual image. So there are two types of images that we can have that can be formed by a mirror or even a lens. We can have a real image and we can have a virtual image. What is a real image? What is a virtual image? So most times in your textbook, even in your school, they tell you real images are caught on the screen. Virtual images are not caught on the screen. What screen are they really talking about? What are we really saying? Real images caught on the screen. What screen exactly? So the first thing, before I talk about caught on a screen or not, is the fact that virtual images are actually produced due to imaginary rays of light. Imaginary rays. Rays that are not actually there are what form virtual images. So this is what we are saying. If I have a plane mirror in front of myself, I have a plane mirror here, and I'm standing in front of the plane mirror, I'm expecting my image to be formed on the other side. I expect my image, so this is the plane mirror, and the boy is standing in front of the plane mirror. The image of this boy will be formed on this other side, on this side of the mirror. This is the mirror, this is the object, then this will be the image. This type of image is what we call a virtual image. And this image is called virtual because it is formed by imaginary rays, rays that are not actually there. Rays that are not actually true, so to speak, are what will form this image here. That's a virtual image. That's one way you can think about a virtual image. The image is formed on the opposite side as the object. The object is on this side of the mirror. The image is formed on the other side. That is a virtual image. Now, if I put a screen here, a screen could be this board. The boy is standing here, then there's a screen behind him or beside him. This is the boy, and this is a screen, which could be this board here. Now, there is a mirror in front of the boy. Let's now assume that instead of seeing his image on the other side of the mirror, his image is formed here. That is what we call caught on a screen. Because remember that there will be reflection of light. So there is a ray of light of the boy going to the mirror and it will be reflected. There's a ray of light of the boy going to the mirror and it will be reflected. Ray of light of the boy going to the mirror, it will be reflected. Now, if the reflection is now forming an image on a screen that is on the same side as that boy, the screen is beside the boy, which is this board, then the image is now formed there. Then this type of image is what we call a real image, because there will be reflection after incidence. There's reflection. This image is actually formed due to true or actual rays of light, not imaginary. Then when we have this type of situation, then that's a real image. But we can't have that type of situation for a plane mirror. If you are in your room and you stand in front of a mirror and you have a board beside you, if your image is formed on that board, instead of seeing yourself inside the mirror, you are seeing yourself beside inside a board that is beside you, then you should run away, because that cannot be a plane mirror any longer. A plane mirror will only produce a virtual image. A plane mirror can only give us a virtual image, images that will be formed by imaginary rays of light, images that cannot be formed on a screen on the same side as the object. That is what we are talking about. So the first kind of image the first property of the image formed by a plane mirror is what? The fact that the image is virtual. Virtual. Now, in the world of optics, as we progress in our optics, because this is the first part that we are looking at, we are going to look at other parts. I'm going to talk about everything as regards optics, but in different videos. Now, as we progress in optics, I'm going to be talking about, we are going to be solving so many mirror equation problems and the likes. And there are important things you should note. And one of the important things is about virtual images and real images. This is the type of image that the plane mirror will produce in terms of type. In terms of orientation, when we say orientation, whether the image will be upright or inverted, any image that is virtual, take note, once an image is virtual, it should give us an erect or upright image. It is important you note these things, because there are some problems that you need to solve, and you need to know whether the image is upright or inverted for you to use the appropriate sign convention to solve the problem. So they might not tell you in your problem that the image is virtual or the image is upright. They might not tell you that the image is upright or the image is erect. Once you are told that the image is a virtual image, automatically it means that it will be an upright image. And the second guy is real. Any image that is real will always give us an inverted image. So we are saying that once the image is virtual, in terms of orientation, the image is what? Erect or upright. Because if you are standing in front of a plane mirror, you will not see yourself upside down now. You see yourself the way you are standing. The image formed by a plane mirror is always erect or upright. And remember again, the idea is this: anything virtual, any image that is virtual must be upright. Any image that is real should be inverted. Number 3. Now, I know some of you will say, okay, but then if I raise my right hand up, I will see my left on the mirror. Is that not what's it called? Is that not saying that the image is inverted? No, the image is not inverted. The image is actually upright. That property that we are seeing, that if I raise my right in front of the mirror, I will see my left. That property is what we call lateral inversion. So the image formed by a plane mirror is actually laterally inverted. It's not a full inversion. It is lateral inversion, which means the right hand side of the mirror of the object will be turned to become the left hand side of the image. If I write a letter P on a piece of paper and show it to a mirror, the mirror will show me something like this. This is what we call lateral inversion. If I raise my right leg, then in the mirror I will see my left leg. That is what we call lateral inversion. So the image formed by a plane mirror is laterally inverted. The next, the image distance from the mirror is same as the object distance from the mirror. The image distance from the mirror is same as the object distance from the mirror. The image distance is same as the object distance from the mirror. That is another property. So if I have my plane mirror like so, and I'm standing at a distance of 5 meters from the mirror, then the image that will be formed here will also be 5 meters from the mirror on the other side. The image distance from the mirror is same as the object distance from the mirror. It is important to know this. So many questions can be asked around this basic concept. The next one is the image size. The image size is same as the object size. The image size is same as the object size. The image size is same as the object size. Very important to know this. So if the object is as big as this, the image will also be as big as this. For a plane mirror, there is no magnification. Of course, there's magnification. So magnification is just 1. That's what we are saying. So and that is the sixth property. Magnification is unity. Magnification is equal to 1. The magnification is equal to 1 for a plane mirror. So these are the properties of the image that will be formed by a plane mirror. It is important to take note of this. The first one is based on the type of the image. The image will be virtual. The second one is based on the orientation of the image. The image will be upright. The next one is a special property for a plane mirror. The image is always laterally inverted. The right hand side will be what? Will be turned to the left hand side. Then the next one is the image distance from the mirror is same as the object distance. Then the next is the image size is same as the object size. And finally, the magnification is equal to unity. And that is because the image size is same as the object size. So the magnification is not greater than 1. Because when we get to curved mirrors now, we are going to introduce magnification. And magnification is just the ratio of the image height to the object height. So if the image height and object height are the same, 10 over 10. What's 10 over 10? 1. That's just what we are saying. So that is why magnification is equal to unity for a plane mirror. So let's go to the next concept. Let's go to the next concept. Let's go to the next concept. All right. So this is the final concept we are going to look at for this part of the lesson, of the video. This is the final concept we are going to talk about for this part of the video. So in our next video, we are going to continue from here and look at curved mirrors mainly. So let's look at this final concept, and that is number of images formed by two mirrors. Number of images formed by two mirrors. All right. So how do we determine the number of images formed by two mirrors? So I'm going to break this into different cases. Case 1. Let's look at the first case. If I have two parallel plane mirrors, we are talking about plane mirrors here, don't forget, not curved mirrors yet. Two parallel plane mirrors. If I have two parallel plane mirrors, this is one mirror, like so. This is another mirror, like so. They are parallel to each other, and an object is placed between them. How many images of this object are we going to see? That is the question. If I have two parallel plane mirrors, just like you go to your barber shop, he's cutting your hair, you are sitting there in front of a mirror, and there's another mirror at the back. Or a dancing room, where there's one mirror here, there's another mirror at the back. That is what we are talking about. How many images will be produced? Very easy. This is the object here. This is mirror 1, this is mirror 2. There's going to be an image that will be formed on this mirror here. The first image on mirror 1, the first one. There will be another image here, first one by mirror 2. This image that is formed there will serve as another object for this second mirror. Meaning that what? Another image will be formed there due to this guy. So there's another image due to the second mirror. This one that is formed there too will serve as the object for this one. Another one will be formed there. Like that, like that. This one will serve as another object to this. Another one will be formed. This one will serve as another object to this. Another one will be formed there. This will serve as another to this. It will continue like that unless there's any form of obstruction. Meaning that the images will continue to what? To form on both sides. Because this image will be an object to this. This one will be an object to this. This will be an object to this. This will be an object to this, like that, like that. Meaning that at the end of the day, the number of images formed will be infinite. Infinity. Except there is an obstacle somewhere. So when two mirrors are parallel, that's the key word. When two mirrors are parallel to each other and an object is placed between them, then there will be an infinite number of images that will be produced by the two mirrors. And that's all. That's the very first case you should know. Please take note of this. Very important. Two parallel mirrors will produce infinite images of what? An object placed between them. Let's look at the second case, and that's all. Case 2. What if the mirrors are not parallel? What if they are inclined at a particular angle? What if they are not parallel? What if the mirrors are inclined at a particular angle? Case 2, case II. Mirrors inclined at an angle theta. Plane mirrors inclined at angle theta. Right? Under this case, I will talk about two different situations again. Situation A. So I have two mirrors inclined at an angle theta to each other, and an object is placed between them. How many images will be formed? The first concept, the first thing we need to do is to obtain 360 degree over theta. Divide 360 by theta and get n. This n is not the number of images produced. Take note of this. We do 360. Let me make this the general guy. 360 degree divided by theta. That's the first thing we do. 360 divided by theta. We divide 360 degree by theta. What's theta? Theta is the angle between the two mirrors. So when we divide 360 by theta and get n, what we get as n will now determine what the number of images produced will be. All right. So the first case here is if n is an even number. If n is even, then the number of images produced, then the number of images produced, let me use as capital letter N, will be this small n minus 1. Whether we are dealing with symmetrical placement or asymmetrical placement. For JAMB guys, over the years, they've been, I think from year 2015 or so, they've just been asking questions on this without telling you whether the object is placed symmetrically or asymmetrically. In fact, I know most of you, this will be the first time you'll be seeing this asymmetrically and symmetrically concept. This is what we are saying. If I have an object here, let's say the angle between this guy is 60 degrees. To place this object asymmetrically between these two mirrors means that we are placing it at a point that is bisecting this angle into two parts. We are placing it in such a way that the object is appearing equally on the two mirrors, symmetrical. We are placing it in such a way that the object is appearing equally on the two mirrors. That is symmetrical placement. Asymmetrical placement means that we are placing it in such a way that it is appearing more on one mirror compared to the other. That is asymmetrical placement. So that means that if our n is even, whether they tell you that it is symmetrical or asymmetrical, it does not matter. The number of images that will be formed, so far as n is even, will just be what? N minus 1. Meaning this 360 degree over theta minus 1. And that's all. Finally, what if it is odd? What if n is an odd number? If this n is odd, what will it be? If this n is odd, what will it be? So the first case, the number of images produced, if this n is odd, will still remain n minus 1 if the objects are placed symmetrically. If your n from here is an odd number, 360 over theta, and it gives you an odd number, then the number of images of the object that will be what? Formed will be n minus 1, just like this first case, if the objects are placed symmetrically. But if the objects are placed asymmetrically, then the number of images produced will just be that n directly, meaning just 360 over theta, without that minus 1. Take note, if your n is odd and the object is placed asymmetrically, the number of images produced is directly 360 minus theta. But if it is symmetric, then you do your normal primary 2, 360 over theta minus 1. But if you are told in your question that it is asymmetric and your n is odd, then you don't need to subtract 1. This is your solution directly. And that is where we're going to stop our lesson for today. I'm very sure that you learned so many things from this singular lesson. We are going to continue from here in the second part, which I'm going to drop very soon. So keep watching. Make sure you share this video with your guys. Make sure you share it across all platforms because I'm still going to be dropping more videos like this on different concepts in physics. So if you are writing JAM, you are writing WAEC, you are writing whatever exam you are writing, so far as there is optics in the syllabus, then this video will be very, very important for you. If you have any question for me, or if you have any topic you want me to talk about again, you can drop it in the comment section. I'm going to look at it and I'm going to do it for you. See you guys in the next video. Bye.